Our objectives for today is to understand some basic chemistry. Now, why is chemistry so vital to the study of biology? In reality, most of biology prior to the last 200 years was, for the most part, descriptive. As we started to understand structure and function, chemistry started to come in. Now, when we look at the characteristics of life, all of the characteristics of life revolve around molecules and chemical reactions. So our review will be directed towards an understanding of, one, the four major macromolecules that make up organisms, which of course are proteins, carbohydrates, lipids, and nucleic acids. And secondly, the chemical environment that allows chemical reactions to take place. In reality, we are, for the most part, biological robots depending on chemical reactions. Now, if you have never had any chemistry, this will be a struggle, and you're going to have to work pretty hard for this. If you've had chemistry, this will be a nice overview, and I strongly suggest that you go ahead and follow through with this presentation. Now, to understand chemistry, we have to go back and start. To start with, let's look at matter. What is matter? For the most part, matter is anything that has mass or takes up space. The desk you're sitting at is matter. The air you're breathing is matter. The water you drink is matter. So everything in the universe is made up of substances that we call matter. All of matter can be broken down into 92 pure substances. Now, these 92 pure substances, each will have its own characteristic, both chemical and physical characteristics. Let's look at these substances. The important ones that you need to understand will be oxygen, hydrogen, sodium, calcium, nitrogen, carbon, phosphorus, sulfur, chlorine, potassium, and magnesium. These elements, for the most part, make up the bulk of living organisms. Now, if you look at calcium, for example, calcium will have unique chemical and physical properties. Carbon will have its unique chemical and physical properties, and so on. If we take a given element and break it down to the smallest part that will still have all of the chemical and physical properties, that little piece is referred to as an atom. So an atom is the smallest part of an element that has all of the chemical and physical characteristics for that particular element. If we look at elements in the universe, especially elements on Earth, we can clearly see on this slide that Earth is made up predominantly of oxygen, silicon, aluminum, a little calcium, some iron, and so on. However, if you look at a human organism, you see that life is made up of hydrogen, oxygen, and most important, carbon. Now that you have a reasonable understanding of what an atom is, can an atom be subdivided? Absolutely. An atom can be subdivided into dozens and dozens of subatomic particles. We will not go into all the weird little critters that an atom can be divided into, but for the most part, atoms can be divided into three major subparticles: protons, neutrons, and electrons. Protons, of course, are present in the nucleus, and they are positively charged. Protons make up the atomic number. Neutrons have no charge. They are also found in the nucleus. Protons and neutrons both make up the atomic mass or weight. Now, the electrons are small, teensy particles that float within shells around an atom. Now, electrons have virtually no mass. They are negatively charged. You will find electrons at various energy levels around a given atom. It is important to understand that all the action when it comes to chemical reactions resides in the space that electrons occupy. So think of electrons as potential energy, and this is really where the action takes place when we will later on see how chemical reactions are performed. Okay, one more thing to emphasize to you that when it comes to the subatomic particles, for a neutral atom, you have just as many protons as you have electrons. So therefore, if you know the atomic number, which is the number of protons, then finally you understand the number of electrons because the two are equal. Okay, now that you understand protons, neutrons, and electrons, please don't confuse croutons. They have nothing to do with any of this stuff. Let's look again at subatomic particles. On your left, we see the simplest atom. And the simplest atom looks, as you can see, it has one proton, which means it has an atomic number of 1. It's got one electron sitting in a shell, an energy shell, and therefore this is a very easy understood atom. And of course, this is hydrogen. If you look at the next complex atom, helium, helium has a nucleus of 2 protons, 2 neutrons, therefore it has an atomic mass of 4. It has an atomic number of 2 because it has 2 protons. Because it has 2 protons, it has 2 electrons. Now, notice that to your right, the maximum number of electrons that helium can have in its inner shell is going to be 2. And I will refer back to this later on. So now that we understand a little bit about the structure of the atom, what do atoms do? Atoms basically form compounds. In chemical reactions, atoms come together to form unique substances called a compound. So compounds are pure substances made from 2 or more elements. If you take a compound apart and find the smallest part of that compound that still has all of the characteristics of that compound, we're dealing with a molecule. So therefore, when we look around at the various substances that we might be familiar with, for example, a lump of sugar would have a molecular weight of C6H12O6. Now, what do we mean by this? When I look at a molecule of sugar, it is made up of 6 carbons, 12 hydrogens, and 6 oxygens, all bound together in a chemical bond that we'll discuss later on. Again, if I look at the molecule water, which is shown to you as H2O, water is made up of 2 hydrogens and 1 oxygen. Next to that, you see methane. Methane is made up of 1 carbon and 4 hydrogens. And finally, we'll look at something that you're familiar with, sodium chloride, simple table salt, NaCl. And that is basically a structural formula for salt. So how are molecules formed? To understand how molecules are formed, we need to understand some basic chemical reactions. I've shown to you reactants producing a product. Substance A plus substance B, the arrow shows you, gives you AB, which is the product. Now, if you look at it with respect to some specific atoms, 1 carbon to your left plus 4 hydrogens produce CH4, which is methane. Further down, we see that 2 hydrogens plus 1 oxygen gives you water. And of course, 1 sodium plus 1 chlorine gives you sodium chloride. Now, the question you have to ask is, what makes hydrogen want to combine with oxygen? And what makes sodium want to combine with chlorine? And so on and so on and so on. Well, the reason for it is that atoms seek stability. And to attain stability, they combine with other atoms. Now, there is something referred to as the octet rule. And the octet rule allows atoms to reach stability. Let's look at some stable and some unstable atoms. To your left, you will see a column of unstable atoms. And to your right, you'll see a column of stable atoms. If you look at hydrogen, hydrogen has an atomic number of 1. That means it has 1 proton and it has 1 electron. The electron of hydrogen revolves around an energy shell, but that energy shell has the capacity of having another electron there. So hydrogen, for it to be stable, would like to get 1 more electron. If it got 1 more electron, it would be stable. It would be very, very happy, actually. Let's look down further at carbon. Carbon has an atomic number of 6, which means it has 6 protons and it has 6 electrons. Let's see where the electrons appear in the energy shell. You can see on the inner energy shell, it has 2 electrons. That's the maximum number of electrons it can have. On the outer energy level, it has 1, 2, 3, 4 electrons. Now, carbon sees itself as being unstable. For carbon to become stable, it has 2 choices. It can lose 4 electrons from its outer shell, or it can gain 4 electrons. Carbon, as you will see later on, will choose to gain 4 electrons, and therefore, if you add the 4 that you have on the outer shell, plus 4 more, and you will have 8, and therefore the octet rule will be maintained. Now, let's look at sodium. Sodium has an atomic number of 11. Now, if you put atomic number of 11, means it has 11 electrons. We'll put 2 on the inner shell, as you can see, just above the nucleus. We'll put now 8 more on the next shell. And guess what? We have 1 extra one that we'll put on the outer shell. This makes sodium extremely unstable. For sodium to become stable, it still would like to have 8 electrons on its outer shell. To do that, it could gain 7 electrons, or lose that 1 electron, which it does in a chemical reaction, and it will end up with 8 electrons. Again, the octet rule is maintained. If you look to your right, you will see that helium has 2 electrons on its inner shell. It is very stable. Neon has 8 electrons on its outer shell. It is very stable. Argon, it has lots of electrons, but if you look carefully, only 8 electrons are present on its outer shell. Therefore, argon, neon, helium are all very stable atoms, and therefore they will not participate in chemical reactions, whereby hydrogen, carbon, and sodium will partake in lots and lots of chemical reactions, some being quite violent. Now, so what type of chemical reactions occur? Now, when we talk about chemical reactions, we're talking about binding of one atom to another atom, chemical bonding. Now, chemical bonding can be broken down into 3 types. One, and before we go any further, remember, all of the action takes place at the electron level. where the electrons are floating around. This is where that action occurs, and you should always realize that not only is there action occurring, but there's some energy transfer working as these electrons are trying to bond with each other, at least sharing space within specific shells. Let's talk about covalent bonding, which is sharing of electrons. We will find that many of the chemical compounds that we will be referring to, covalent bonding is going to be very, very important. Now we'll look at ionic bonding. Ionic bonding is basically going to be a transfer of electrons to form ions. Now, ions, as you will see, are charged atoms or group of atoms. And then finally, we will look at hydrogen bonding, which are important in protein formation. There are weak bonds between slightly charged hydrogen and some other negatively charged entity. First, let's look at covalent bonding. Covalent bonding in the formation of water. Water consists of the molecule H2O. Now look at this funny looking structure. It looks like an upside down Mickey Mouse. Now this structure has one oxygen and two hydrogen. Now the reason this forms is because oxygen, as you can see, has an atomic number of 8. That means it has 8 electrons. 2 electrons will go on the inner shell, and 6 electrons will go on the outer shell. So therefore, oxygen would like to get 2 more electrons. And guess what nature has provided? 2 hydrogens that come in. Each of the hydrogens would like to gain 1 electron. So 1 hydrogen comes in on one side, 1 comes in on the other side, and each donates 1 electron to the outer shell of oxygen. So that oxygen now perceives itself as having 8 electrons and is happy as a lark. Hydrogen is also happy because it now perceives to have 2 electrons on its inner shell. Therefore, both oxygen and hydrogen are happy, and a molecule of water is formed, which is the essence of all living things. Without water and the characteristics of water, we would not be alive carrying out this activity. Okay. Now, covalent bonding is important in many structures, as we will see later on. But let's look at covalent bonding in the formation of polar and nonpolar molecules. The reason that water is such an important entity in life is because it forms this Mickey Mouse structure, as we will see in a moment, is a polar molecule. Now, look to your left. You see the water molecule, and you see that towards the top, it has a field of electrons. Therefore, it's going to be slightly negatively charged. Towards the bottom, we have these 2 big protons that stick out that belong to hydrogen. Therefore, it gives the molecule a slightly positive charge. And the result is that you have a slightly negative charge on the top, a slightly positive charge on the bottom, and this becomes a polar molecule. And we will see later on how this polar molecule gives water all the important characteristics that will maintain life. Now, if you look to your right, you will see a nonpolar molecule formed by covalent bonding. Here we have carbon, which has a need for 4 electrons. 4 hydrogens come in and donate an electron. The end result is a very, very stable molecule of methane gas. Now, notice that this molecule is extremely balanced. It does not have any negative charges or positive charges towards one side of the molecule or the other. It is pretty much symmetrical. So again, covalent bonding can lead to the formation of polar and nonpolar molecules. Let's continue this review and look at how molecules are organized and how they're illustrated. First of all, when we look at ammonia, which is NH3, one nitrogen, three hydrogens, you can write it as NH3 as the molecular formula. You can draw it as N with a line going to the hydrogen, another line going to the other hydrogen, and one line going down. Each line represents two electrons that are bonded. So therefore, every line you see represents a covalent bonding of two electrons. And of course, you see to your right several other models which are not that useful for our purposes. Let's look now at the second type of bonding that takes place, called ionic bonding. In ionic bonding, we're going to be forming ions. As we said before, ions are charged atoms or groups of atoms. Let's form the compound salt. If you look to your left, we have sodium, which has one electron sticking out there. We have chlorine, which has 7 electrons on its outer orbit. Remember the octet rule? An atom reaches stability if it has 8 electrons. So for sodium to become stable, it will lose 1 electron. And for chlorine to become stable, it will gain an electron. And when this happens, sodium is happy, chlorine is happy. But when sodium loses an electron, it becomes positively charged. And when chlorine gains an electron, since electrons are negatively charged, it becomes a negatively charged particle. So sodium is positively charged, and it becomes an ion. Chlorine is negatively charged, and also becomes an ion. The two now see each other, and they become attracted, and you can see what happens. The two come together, forming a little cube of common salt. Sodium positive, chlorine negative, hanging in together by ionic bonding. And finally, we get to hydrogen bonding. Hydrogen bonding are weak bondings between hydrogen and other compounds, important in proteins and nucleic acids, and basically give water its characteristics. And finally, we get to hydrogen bonding. Hydrogen bonding are weak bondings between hydrogen and other compounds, important in proteins and nucleic acids, and basically give water its characteristics. So let's look at hydrogen bonding as related to water. If you remember, water is a polar molecule, slightly negatively charged on one side and slightly positively charged on the other side. When the water molecules see themselves, they attract themselves because the positive charge of the hydrogen will see the negative charge of the oxygen and slightly bond itself. And as you can see, this lattice formation is formed, giving water its unique characteristics.